Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there's no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition, and we are doing problem number 5.20. The problem statement says a tank in a room at 19 degrees Celsius is initially open to the atmosphere on a day when the barometric pressure is 102 kilopascals. A block of dry ice, solid CO2, with a mass of 15.7 kilograms is dropped into the tank, which is then sealed. The reading on the tank pressure gauge initially rises very quickly, then much more slowly, eventually reaching a value of 3.27 megapascals. Assume a final temperature of 19 degrees Celsius. Part A. How many moles of air were in the tank initially? Neglect the volume occupied by CO2 in the solid state, and assume that a negligible amount of CO2 escapes prior to the sealing of the tank. How many moles of air were in the tank initially? Okay, so this is our initial state. We've got our tank here. First, it's at 19 degrees Celsius, and it's at the barometric pressure, and it's all air. Okay, then we drop this volume in. We know that it has a certain mass, and put that into the tank, but we don't care what the volume of this is because they said it's negligible. Okay, so it doesn't actually occupy any volume in the tank as a solid. Okay, so then part 3, we've let all of the CO2 and air turn into a gas and mix together, and there's a certain amount of mass of CO2 in here, and it's the same amount of mass that we put in. Okay. Then we've got same temperature, and then we also have the much higher pressure, right? Because now there's a bunch of CO2 in here as well. Okay, so part A, it says how many moles of air were in the tank initially. Okay, initially how many moles of air? Well, we can't solve for what that is using the ideal gas law because we don't know what the volume of the tank is. Right? So we're kind of stuck. So we need to use all the rest of this information that we have in order to calculate what the volume of the tank is, and then we can calculate what the number of moles of air is in there. Something that will give us a clue is that, okay, we started off with a certain pressure, and then the pressure built to a certain amount after we added this CO2, so that this relationship of a certain number, a certain pressure that built after we added a certain amount of CO2, that is the key to getting what the volume of the tank is. Okay, so assume that the volume of CO2 solid is negligible. Okay, perfect. So in state 3, how many moles did we have? Oh, well, this is moles of CO2. Okay, so how many moles of CO2, right? Because they gave us a mass of CO2. Well, we're doing all of these calculations in moles, so we just need to convert that over into moles. So this is the molar mass of CO2. And using the molar mass of CO2, we can calculate that there are this many moles of CO2. Because this is the mass of CO2 that they gave to us. Right, they said there was this many kilograms. We need to convert that into grams, so those cancel out, right? And then we get this many moles of CO2. All right. Okay, so how many moles of air then are in tank 3? Because now we know how many moles of CO2 are in there. Well, it's however many moles there are total in there minus how many moles of CO2 are in there. That's how much air is in there. Okay, and then we also have the ideal gas law we could use for how many moles are in state 3. Ideal gas law, because we know the pressure and we know the temperature, we don't know the volume of the tank, obviously, so we can't actually calculate how many moles are in state 3, but we do know this density ratio, right? So that might come into handy. And then in state 1, we also don't know this density ratio because we don't know volume, so we can't actually solve for n. But we do know the temperature and the pressure. Okay, so we multiply those out and we say all this equals A, because I don't want to write down the number every single time I need to use it, and then this equals B. Okay, so now we have 3 equations and 3 unknowns, it looks like, right? So we've got these equations, and they're pretty simple equations, so I'm just going to go ahead and rewrite the ones that we know down here. Okay, so equation number 1, there's 2 unknowns, and then equation number 2, there's 2 unknowns, and equation number 3, there's 2 unknowns. Okay, so the unknowns are n1, n3, and the volume, and we have 3 unique equations. Okay, so that's 3 equations, 3 unknowns. We know how to solve those. We just use linear algebra or substitution or whatever, and we can solve for each of the 3 unknowns. Okay, so I do that off screen here. We solve for the number of moles in both states, and then we also solve for what the volume is. Okay, what they asked us for in part A was how many moles of air were in the tank initially, right? So that is how many moles of air were in the tank initially, N1, okay? And we got that by solving for the volume as well. Okay, part B. What is the final density, grams per liter, of the gas in the tank? Okay, final density in grams per liter of the gas in the tank. Well, density in state 3 is equal to the mass over the volume. Okay, and the mass is equal to the molar mass of state 3, whatever that is, times the number of moles in state 3, which we already calculated up here, and the volume, which we already have right there. Okay, so all we really need to know is what's the molar mass of the gas in state 3. Well, the molar mass of the gas in state 3 is equal to the weighted average of the components. Each component, carbon dioxide, oxygen, and nitrogen. Okay, so we need to know the molar masses of each of these. Molar mass of carbon dioxide is this, oxygen is this, nitrogen is this. Okay, but the component that we're missing is the mole fractions. So we need to solve for the mole fractions. What are the mole fractions? Mole fraction of carbon dioxide is the number of moles of carbon dioxide, which we do know from earlier. Number of moles of carbon dioxide, we solve for that. Per N3, we know N3 because we solved for it here. Okay, so that's the number of moles of carbon dioxide. Then we need to know what the molar mass of air is. We already solved for the molar mass of air. It's in the same ratios as what air is normally in. Oxygen has a mole fraction of 0.21, and nitrogen has a mole fraction of 0.75. So the remaining amount, air, is going to have this ratio, because it's going to make up the difference of how much is not carbon dioxide. Okay. So that's how you solve for all of the molar masses for each of those components, and then you do the final bit here and multiply all those together, do the weighted average, and you get that the molar mass of the gas in state 3 is slightly less than carbon dioxide, right? Carbon dioxide is 44, this is 43. That's because most of it is carbon dioxide, so it's going to be heavy. Okay, so that means the density, going back up here, density up here, remember all we needed was the molar mass. Okay, so you just multiply all those together and you get 58.6 grams per liter. I made sure to do the units so that you guys could see and convert it into grams per liter, because that's what they asked for. Okay, part C. Explain the observed variation of pressure with time. more specifically, what is happening in the tank during the initial rapid pressure increase and during the later slow pressure increase. Okay, part 1, fast temperature increase. Cold solid plus warm tank equals ice turning into carbon dioxide. So that's just the sublimation process. That's going to happen pretty quick because you're at room temperature, the tank's at room temperature, and the ice is very cold. When I say ice, I'm talking about the solid CO2. That is very cold. So that CO2 is going to heat up pretty rapidly, or at least phase change very rapidly into a gas. Okay, so that means that the tank is going to get cold. All the gas in that tank is going to get cold, but it's not going to be so cold that not all the ice will turn into a gas. So all that ice is going to turn into a gas, but it's going to be really cold in the tank still, right? So the temperature is going to be very low. It's going to be high enough that all the ice turns into gas, but the tank is still going to be pretty cold after all that ice sublimates. Okay, so cold tank plus warm room, but that tank is sitting in a warm room, right? And so over time, that tank is going to warm slowly up to room temperature, and as the temperature is increasing, that CO2 is going to heat up, and the tank pressure will build very slowly as that temperature increases up to room temperature. Okay, so that explains the initial solid to gas transition, fast, rapid pressure increase, temperature increase from low temperature to room temperature is going to be very slow. That's the slow increase. All right, well, that is it for problem number 5.20. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again. I'll see you in the next video.